We've seen first derivatives determine the increasing and decreasing nature of functions, and we've seen first derivatives determine critical points. We've also seen second derivatives determine concavity, but that's not all that they can determine. We can see that with concavity and critical points together, we can tell if there's a maximum or minimum. And that's the nature of the second derivative test, okay? So I'm going to call that the second derivative test, all right? And I'm going to explain to you visually what it says before I explain to you what it means algebraically, or what it's saying. So remember that if f double prime at some point c is greater than 0, the function is concave up at that point c. So it's up like a cup like this. And here's your, for any c within the interval. Now if c is a critical, that is, the function is going to be basically equal to 0 when you take the derivative of that. So again, just remind you here, this is x, here's f of x, not f prime. Here's our function. It's concave up because the second derivative is greater than 0. But also the first derivative here at this point c is going to be equal to 0. So when c is a critical and the function is concave up when c is in that interval, we see that c is a minimum. All right, and that's what the second derivative test determines here. That, let's say, if c is a critical, all right, if c is a critical of f, then when f double prime of that point c is going to be greater than 0, we see a minimum. So c is a minimum, or f of c for that matter, is a minimum. All right? And that's an important thing to convince yourself that's true. Now let's take a look at f double prime of c is less than 0. All right? That means it's concave up, right? Or sorry, this is greater than 0, concave down, right? So if f double prime of c is less than 0, then f itself is concave down. So here's f of x, all right? It's concave down like a frown. And if c is within that interval where it's concave down, and it's a critical point, then you can see here that it looks like a maximum. So again, that means here, f double prime of c less than 0 is going to tell us that f of c, the actual function f of c, is a maximum. And that's really cool because you don't even have to rely on the idea of a graph's pictures. You can tell right away and classify which points are maxima and minima. All right, and don't get confused by the fact that the double prime of c is greater than 0 is a minimum, and then the less than 0 is a maximum, okay? They just have to do with concavity. That's the thing you should be thinking about when looking at the second derivative test. It's concavity. All right, so let's try that on for size. And let's find the process of how to do this. All right, let's find all the critical points of sine cubed of x from negative pi to pi. Now, we don't know what sine cubed of x looks like, so we can only rely on our knowledge of derivatives for this. All right, so we want to find all criticals. Find label as maxima or minima or inflection points, all criticals of sine cubed x on the interval negative pi to pi. So the first thing you want to do, okay, step 1, is take the derivative. All right, take the derivative. I'm going to write that out. All right, so if our function f of x is equal to sine cubed of x, like this, then f prime of x is equal to, all right, the derivative with respect to x of sine cubed x. And by the chain rule, we just hop that 3 down and we get 3 sine squared x, like this, multiplied by the derivative of the inner function sine x, which is cosine x, like this. So we get 3 sine squared x cosine of x as the derivative. And what we're going to do is we're going to set that equal to 0, all right? We're going to say equal with a little set on top. That's my notation there. Set to 0. And now what we're going to do is we're going to find all the points x within our interval negative pi to pi that satisfy the fact that this is equal to 0. And you can think about these right away. We can see we have x equals 2. So when is cosine negative in the interval? Well, it's going to be negative at points negative pi over 2 and pi over 2. So pi over 2 and pi over 2 are 2 examples. But then we also have the sine squared. Well, sine is going to be 0 at the points 0, negative pi, and pi. So here you go. All right. So now that we've found all of our critical points, we have to identify them as maxima or minima. All right. And so what we're going to do is step 2, take the second derivative. Take the second derivative. All right. So that's what we're going to do. We're going to take the second derivative, and we're going to check by plugging in values of our critical points into the second derivative and see whether they're positive or negative or 0. All right, so let's do that. So we have to do d squared over dx squared of sine cubed x. And we've already taken that derivative once, so that this is equal to the derivative with respect to x, the regular first derivative, of that function right over here, 3 sine squared x cosine x. All right? 3 sine squared of x cosine of x. And by the product rule, we can do this really easily. So we get equal to, f prime here is 3 sine squared x, which becomes, let's see, we have the 6 times sine of x cosine of x times that cosine of x over here makes cosine squared of x, and add that to g prime f, we get plus, well, this is negative sine x times 3 sine squared x, so we have minus 3 sine cubed of x. So there you go. That's the second derivative. All right? And what we're going to do is actually kind of, wait, let's see, did I do that right? Yeah, I think so. Yeah. All right. So what we get is 6 sine x cosine squared x minus 3 sine cubed x. You can factor out the 3, whatever. But now we're going to see what this is equal to by plugging in negative pi over 2, pi over 2, 0, negative pi, and pi. So as you can see right away, if you plug in 0, then the sign is going to become 0. And the same thing happens with negative pi and pi. So 0, negative pi, and pi all fail that second derivative test. All right? So I'm just going to tell you right now that upon further analysis of this function, you're going to see these are all inflection points because these are points where the function changes concavity. And I encourage you to go on Desmos and take a look at this function itself, sine cubed x, and looking at the behavior at those points. But at negative pi over 2 and pi over 2, we see something different. If you plug in negative pi over 2 in here, yes, the cosine squared makes this entire term go to 0, but negative pi over 2 here gives you negative 1, and then you cube that becomes negative 1. So then you have negative 1 times 3, which becomes positive 3. And so the function there is greater than 0, the double prime, which means that since the second derivative is greater than 0, then negative pi over 2 is going to be a minimum, a min. And I'm just going to label these as inflection points. All right? And now you might logically guess that pi over 2 is a maximum, but let's check that. So again, this entire term goes to 0 because of the cosines, but here we have negative 3 sine cubed of pi over 2. Well, sine of pi over 2 is 1, and cube that you get 1, so you get negative 3. And of course, negative 3 is less than 0, which means that, yes, indeed, pi over 2 is a maximum. And there you go, you've just classified these points as maxima or minima. And in fact, then you can also take the second derivatives and look at the concavity, and you can take a look at where it's increasing and decreasing to fully graph sine cubed of x on the domain of negative pi to pi, all right, on that interval. All right, so that's really interesting. You can use the second derivative not just to find concavity, but with that, you also get the idea of when points are maxima or minima if they're criticals within that area where they're concave up or concave down. But now I want to gravitate towards another very interesting thing. The second derivative test, you might be wondering, is there a third derivative test? All right, and in fact, there is such a thing as the third derivative test. All right, the third derivative test, and it's not exactly what you'd expect, okay? So we're going to use a visual argument from the previous video to find out what the third derivative tells us about a function. So again, if f triple prime of x, or some point c, within an interval, is greater than 0, what does that mean on our little number line here? We have x and f of triple prime here. All right? Well, that means that on a certain interval a to b, it's always positive, like this. We can give that example. So then, working our way backwards, f double prime of x on that interval a to b, well, because it's always positive here, then that means that it's strictly increasing, right? The derivative of this is positive on this interval, which means that this function itself has to be increasing. So we see a sort of increasing behavior like this. All right? Then we go to f prime of x. Now, if f prime of x has the derivative that's going to be strictly increasing, it has some negative parts, as you can see here, and some positive parts, which means it's going to be able to have this behavior. Let's sketch that out real quick. So because this part's negative, on this point here, let's just call this point, let's see, D, all right? Then from A to D, you can see that this part is going to be decreasing, sorry. So let's draw that out because it's always negative, the value. And then, because it's 0 here, D is a critical point, and from D to B, you see it's increasing because it's positive. So I'm actually going to draw this a little bit better. It looks something like, maybe like this. Okay, so you could do that, or you could do something like this, right? It really doesn't matter. So that's a better example. And now let's look at the actual final f of x function, the one we want to know what the third derivative tells us about that function. Okay? And working our way backwards, we're going to see from a to b. What do we get? Well, at this point here, I'm going to call this e. I'm going to call this point f because we want to find out these areas. So from a to e, we see the function itself is positive, which means from a to e, f is increasing. All right? So maybe it's doing something like this. But at e, it's become 0, so we get a critical point. And then from e to d, or actually from e to f, the whole values of the f prime are negative. So all the way from e to f, all right, which is somewhere like here, the function is decreasing. So we see it like this. But at f, it becomes a critical point, so it's equal to 0, the tangent. And so then from f to b, it's positive, which means it's increasing, like this. And now we're done. We've graphed a general view of what our function could look like. And so the f triple prime of c tells us an important fact. Notice that this function changes concavity. It's concave down here and then concave up over here, which means that at some point within this interval, there is an inflection point. And so that's what the third derivative tells us, that this original function changes concavity somewhere within that interval. And so that means that there's an inflection point. Now, I encourage you to try the same argument for f triple prime of c is less than 0 and kind of convince yourself that it's true for both when f triple prime of c is both greater than or less than 0. In either case, as long as it's not 0, you will get that there's an inflection point somewhere in that domain or interval. And so let's run some examples. You have f of x equals x cubed, okay? When you take the derivative of that, you get 3x squared. You plug in 0, you know there's a critical point at 0, all right? So we have a critical at 0. And then if you take the derivative of that again, you get 6x. But if you plug in 0 to that, you don't get a max or min, you get 0, all right? Which means we failed that test. But let's just take the third derivative. We get 6, and that's greater than 0 because that doesn't depend on the actual x variable. And so that means that because that's positive, that this function changes concavity at that point 0. And so that means that 0 is in fact an inflection point, and we know that it's an inflection point when we graph x cubic. So let's see, we have this, and there you go. Over here at 0, 0, it's an inflection point, and the third derivative tells us that. Now, the important thing to notice as well is that there are some cases where even this will fail, and the higher order derivative test won't actually tell you much about the function. If I take f of x equals x to the fourth, all right, we know that this function is going to be concave up like a cup for its entire domain. And yet the derivative tests don't tell us anything about what happens at 0, which is obviously going to be a global minimum. So just be careful when relying on your intuition and when relying solely on those points and derivative tests. You want to make sure you really use your own deeper gut feelings to determine where things are positive, negative, where things are absolute minima or maxima. Now, this also motivates the idea of the nth derivative test, because again, third derivative test can also equal 0. So the nth derivative test, okay, will tell us something very important. If we keep taking derivatives of a function where if you plug in the critical point it's equal to 0, if you keep taking derivatives until the first time that the derivative is going to be non-negative, non-zero, you know there's an inflection point. So let's just take an example of the function x to the n, all right? Or x to the fifth, let's say. If you take the derivative of that and you get 5x to the fourth and you plug in 0, you get 0, you fail. All right, take the derivative again, you get 20x cubed. Again, you fail there. And so let's do it again. You get 60x squared, plug in 0, you fail again. So you want to take the derivative again. So that's 1 derivative, 2 derivatives, 3 derivatives, 4th derivative, you get 120x, and you plug in x equals 0, and you still get 0. Let's take the 5th derivative, all right? That's the nth derivative here. You get 120, which is positive. And so that means that there is, in fact, an inflection point. That function changes concavity at least once within that interval. And in fact, we do see that x to the 5th has an inflection point. Because remember, it looks something like this. All right? As you can see, it's concave down from negative infinity to 0, and concave up from 0 to infinity. So again, I hope you understand a bit better about how these derivative tests are so important and why they're so important. The most important takeaway here, however, is the fact that first derivatives give us information about critical points and increasing and decreasing natures of functions. Second derivatives give us information about the concavity of these functions at certain points. And then we have higher order derivatives that give us information about the changing of that concavity. So another analog to the derivative, that change. So the idea here is that a function's derivatives contain so much hidden information about that function itself, which is fantastic. You don't even have to know what the graph of a function looks like to graph a general idea of it with the help of your derivatives. And this leads to the idea of possibly expressing a function in terms of its own derivatives. And that's a really interesting thought, which you might see at the end of a calculus course. Till next time.